Hi guys, in the last lecture we covered how the power flows in an induction motor and we saw different type of constructions of the induction motor, squirrel cage and wound rotor. We have also seen what are the different speeds at which different fields rotate in a induction motor, that is the rotor magnetic field and the stator magnetic field. We looked at different relative speeds of these fields with respect to different parts of the induction motor. In this lecture what we'll do is we'll see some problems that have appeared in GATE examination from this topic. Okay, so let us start with our first problem. It is saying the direction of rotation of a three-phase induction motor is clockwise when it is supplied with sinusoidal voltage having a phase sequence ABC. For counterclockwise rotation, the sequence of power supply should be. As I told you, whenever the supply is applied on the stator, the motor behaves as an induction motor, and when it is applied on rotor, it behaves as inverted induction motor. In case of induction motor, rotor rotates in the same direction as the field. That means if it is supplied with phase sequence ABC, the field is rotating clockwise. Okay. So field rotates clockwise. For anti-clockwise rotation or counterclockwise rotation in an induction motor, the direction of rotation of the field must be reversed. That is, field must rotate anti-clockwise now. To reverse the direction of rotation of field, we must reverse the phase sequence. As we saw in synchronous machine, whenever the phase sequence is reversed, the magnetic field generated rotates in a direction opposite to the initial direction. So we can use the phase sequence ACB. ACB. Or we can use BAC, CBA. So these three phase sequence will be a part of negative sequence. Okay. So to reverse the direction of magnetic field, we use a negative phase sequence, and for the same direction we use the positive phase sequence. So that is how we can reverse the direction of motor rotation. Moving on to the next problem. It is saying a three-phase wound rotor induction motor is to be operated with slip energy in the constant torque mode when it delivers an output power P0 at slip S. So this is the mechanical power, which is P0. Slip is given to be S. The maximum power that is available for recovery at the rotor terminals. See, the power that can be recovered is actually it is only possible in case of wound rotor induction motor. This power is recovered at the slip rings. Okay. This power is actually S into PG. Okay. This power is usually lost in the copper losses in case of a squirrel cage induction motor, but it can be recovered at the terminals of slip ring in case of wound rotor induction motor. Now we know mechanical power is Pg into 1 minus S. Then Pg becomes P0 upon 1 minus S, because Pm is P0. That means recovery power would be S into P0 by 1 minus S. Okay, because it is S into Pg. So remember, there are two outputs in case of a wound rotor induction motor. One is the electrical output at the slip ring terminals. One is the mechanical load that is connected to the shaft. So whatever is the power across the slip rings is called as recovered power, or it is called as slip power recovery scheme. It is one of the methods of speed control of an induction motor. Moving on to the next problem. It is saying a 400 volt 50 Hz 30 horsepower. So this horsepower is the mechanical output rated of the motor. It is drawing 50 ampere, so input current and input power factor. So what I have been given is input voltage, input current and input power factor. So from this data what I can determine is the input power. Then the stator and rotor copper losses are 1.5 kilowatt and 900 watt. Friction and windage loss are 1050 watt and core loss are 1200. What is the air gap power? Now, since I have been given the data to calculate the input power, I will calculate the air gap power from the input side. So first let us calculate input power. Root 3 VL IL cos phi root 3 into 400 into 50 into 0.8. So how much will this come? It will be 27.712 kilowatt. Now I know we must subtract stator copper loss and core loss from the input power. That is 27.712 minus stator copper loss are 1500, core loss are 1200. So this will be 25.012 kilowatt. Okay. So this must be taken in kilowatt. So write it as 1.5 and 1.2 instead of watts, because this power is in kilowatt. Okay. So this will be 25.012. Then to calculate mechanical output, we need to subtract the rotor copper loss from this equation. So if I wanted to calculate PM, that is the mechanical developed power, it will be PAG minus P rotor copper. And for shaft power, it will be mechanical minus rotational loss, which is the friction and the windage loss. Okay. So you must remember where each and every loss occurs in the system, then only you will be able to calculate any desired power. And just look at the problem statement carefully to know whether to proceed from the shaft side of the motor or from the input terminals of the stator. In this question, I was given the current drawn by the stator, so I proceeded from the stator side. If I would have been given the output power, or I would have said that the motor delivers the rated load, that means motor output power is 30 horsepower, then we will approach from the shaft power side and we will add the losses to obtain any power. Okay. If it would have said the motor delivers a rated load. In our next problem, it is saying the power input to a 415 volt 50 hertz 6 pole 3 phase induction motor running at 975 rpm is 40 kV. See, first of all, whenever you see this frequency in poles in this, you must calculate synchronous speed. 120 into 50 by 6, 1000 rpm. I have been given actual speed, that is 975 rpm. So I can calculate based on this the slip. 1000 minus 975 by 1000, that is 0.025. Now I have been given the stator losses are 1 kilowatt, friction and windage are 2 kilowatt. So to calculate air gap power, I must subtract stator copper loss from the input power. 40 minus 1, that is 39 kilowatt. Now this is the air gap power. I know the slip, so I can calculate mechanical power. It is air gap power into 1 minus S, that is 39 into 0.975. So this power comes out to be 38.025. To calculate the efficiency, we need the final output of the machine. Final output is the shaft power. Shaft power can be obtained from this. It will be 38.025 minus rotational loss, that is 2 kilowatt. 36.025 kilowatt. Now efficiency is output. Output is 36.025 upon input. Input is 40. So this becomes 90.0625%. So that is the efficiency of the induction motor. Okay. So just proceed from input to output based on the given data. Here again we were given the input power. Okay, let's move on to the next problem. It is saying a center zero ammeter connected in rotor circuit of a 6 pole 50 Hz motor makes 30 oscillation in the 1 minute. Center zero means the zero reading lies at the center. Okay, and if it is making oscillation of 30 oscillation per minute, means the frequency of rotor is 30 rpm. Okay, or we can say 0.5 revolution per second, or we can say 0.5 hertz. Now we know rotor frequency in case of induction motor is S into F. It is 0.5. So stator frequency is given to be 50, which implies slip is equal to 0.01. Okay. So rotor speed can be calculated as ns into 1 minus s. So ns we need, ns will be 120 into 50 by 6, which is 1000 rpm. So this will be 1000 into 1 minus 0.01, which is 990 rpm. So rotor rotates at a high speed near to the synchronous speed, that is 990 rpm. Okay. So whenever you see the data of the poles and the frequency, first thing that must come to mind is calculating the synchronous speed. In our next problem, it is saying the rotor power output of an induction motor is 15 kilowatt and corresponding slip is 4%. Rotor power output means, since we are not given any mechanical losses, I will consider the output power is equal to mechanical developed power, which is equal to Pg into 1 minus S. It is asking the rotor copper loss. We know the rotor copper loss is S into Pg. So it will be S into Pm 1 minus S, which we derived in one of the problems also. So S is 0.04, 1 minus S will be 0.96, and Pm is 15 kilowatt. So it will be 625 watts. So this will be the rotor copper loss in case of an induction motor. Okay. So these formulae for the rotor copper loss and the mechanical developed power in terms of air gap power are very important for solving the numericals. Let us move on to next problem. It is saying a 6 pole 50 Hz wound rotor induction motor, when supplied at rated voltage and frequency with slip ring open circuited, developed a voltage of 100 volt between any two rings. So this is actually the line voltage between the at the rotor terminals under open circuit condition. Okay, or we can say it is the induced EMF line to line at the rotor side. Now rotor is being driven at 1000 rpm opposite to the stator field. We need to find frequency across the slip rings. Now first let us calculate the synchronous speed. 120 into 50 by 6, that is 1000 rpm. The rotor speed is opposite to synchronous speed, so I can write down minus 1000 rpm. So if we calculate slip, ns minus nr by ns, it will be 1000 minus 1000 by 1000, which is 2. So slip ring frequency is rotor frequency, which is S into F. 2 into 50, it will be 100 Hertz. Okay, so we have stepped up the frequency, or we have increased the frequency by the use of an induction motor. That is how it is being used as a frequency changer. Let us look at the last problem. The stator and rotor of a 3-phase 4-pole wound rotor induction motor are excited from 50 Hz and 30 Hz source. Neglecting all losses, what are the load speed at which the motor would run? So rotor frequency is 30 Hz. Stator frequency is 50 Hz. So slip will be 30 by 50, which is 0.6. Now we can calculate synchronous speed. 120 into 50 by 4, which is 1500 rpm. So 0.6 would be ns minus nr by ns, or we can say nr would be ns into 1 minus s. So it will be 1500 into 0.4, that is 600 rpm. We can also consider the slip to be minus 0.6 to calculate another possible speed of the rotor. Okay, the negative slip indicates the operation of the motor in the generating region. That is, it behaves as an induction generator. 1500 minus nr by 1500. From here nr comes to be 2400 rpm. If the rotor is driven at a speed of 2400 rpm, it will again have a frequency of 30 Hz, and if it is driven at a speed of 600 rpm, then also it will have a slip frequency of 30 Hz. So remember, whenever the speed of the induction motor is asked to you for the given rotor frequency, do consider both the cases of positive and the negative slip. Okay, so that is how we solve these kind of problems. So in the next lecture, what we'll do is, we'll see how the torque varies with speed in case of induction motor, or how the torque varies with slip in case of induction motor. Those are called as torque slip characteristics. That is the most important part in this chapter.